I posted the midterm review yesterday, but I forgot to unlock it in the files. So if you couldn't access it, if you tried to look at it yesterday, it is now fixed. So you can see it on Canvas. Any questions? So we were talking on Monday about the cylinder in crossflow and how you have upstream of the cylinder, you have this stagnation point where the fluid comes to a complete rest, and then the flow moves under a favorable pressure gradient around toward the top of the cylinder. You reach some minimum pressure there, and then the flow is moving further past the cylinder under an adverse pressure gradient. So it's being kind of pushed forward by the pressure and then pushed backward by the pressure as it goes around the cylinder. And we talked about how that contributes to boundary layer separation at some point behind the cylinder, or kind of toward the top of the cylinder, and how that creates a wake downstream. We discussed that the boundary layer separation is, the point of separation is influenced by whether the flow is laminar or turbulent. So a turbulent boundary layer tends to have more momentum due to turbulent mixing, so it can stay attached for longer. And we said that there's this kind of defining Reynolds number for the cylinder in crossflow of 2 times 10 to the 5th. And if the Reynolds number is lower than that, the boundary layer remains laminar, and so it detaches earlier on at approximately 80 degrees, so just before kind of the exact top of the cylinder. And then if it's greater than 2 times 10 to the 5th, boundary layer transition occurs, so the boundary layer becomes turbulent, and then separation is delayed until about 140 degrees. So that results in a much narrower wake because the boundary layer separation is delayed until well past the top of the cylinder. So today we're going to continue talking about that and then write down some expressions for the Nusselt number for a flow over a cylinder. So this is just cylinder in crossflow continued. So we typically talk about how the flow conditions affect both the friction coefficient and the Nusselt number. And we'll talk about kind of those two aspects for a cylinder as well. So unsurprisingly, boundary layer development and separation influence the drag force on a cylinder. So previously, talking about flow over a flat plate, we've only really talked about drag in terms of the friction coefficient that's coming from the skin friction on the plate. Because we now have a wake behind the object, that's going to introduce a new type of drag. So now there's 2 types of drag or friction that contribute to the overall drag force. So here, there's 2 components of FD, drag force. The first component is the same as what we talked about before for flow over a flat plate. So it's skin or friction drag That's due to the shear stress between the surface and the fluid right at the surface. And this is what we have been determining previously, and this is what is determined from C sub F, that friction coefficient that we've been writing down, that has like the shear stress in the numerator. The second type of drag that's caused by the formation of a wake behind the cylinder is called form or pressure drag. And it is due to the pressure differential in the flow direction resulting from the wake. So we have a kind of higher pressure upstream of the cylinder and a lower pressure downstream of the cylinder in the wake. And if you have a pressure differential, if you have, say, you had a cylinder that was kind of floating and wasn't fixed, if you had a pressure differential, it would be pushed one direction, right? It would be pushed in the direction of lower pressure. But because we're talking about kind of a fixed object, we have this pressure differential that's maintained in the flow, and so that, instead of moving the object, it's exerting an extra drag force. So that's how that pressure difference kind of shakes out. So the combination of these two types of drag is expressed in this overall drag coefficient, C sub D. So note, C sub F is just the friction drag, C sub D is the total drag of the two types. And that's the total drag force divided by the frontal or projected area of the cylinder times rho v squared over 2. So that's v squared, rho v squared divided by 2. And this, A sub F, is the frontal or projected area in the flow direction. So if you're looking at the cylinder as the flow would be directly on, then for a cylinder it's just the diameter times the length, right? So the projected area of the frontal part of the cylinder. So the laminar and turbulent boundary layers have different effects on the different types of drag. And we talked about how laminar versus turbulent boundary layer affects the friction drag differently. And it's the same as for flow over a flat plate as it is for a cylinder. But for the pressure drag, a transition to turbulence delays separation, and we said this results in a narrower wake. and therefore significantly decreases the pressure drag. So if the boundary layer stays attached longer, you have a narrower wake, then there's a much smaller region of the lower pressure behind the cylinder. And so it's reducing that pressure or form drag. And all of these dynamics, boundary layer dynamics, of course, also influence the Nusselt number because they influence the temperature distribution around the cylinder. So we have an expression for the local Nusselt number just at theta equals 0, kind of right at the stagnation point. And then we'll also write down an expression for the average Nusselt number over the entire cylinder, which is what will be more commonly used. And that's assuming that you have both laminar and turbulent regions. So we'll say the local Nusselt number just at theta equals 0 is 1.15 times the Reynolds number. Remember, we're talking about diameter-based Reynolds number and diameter-based Nusselt number here. So the characteristic length is the diameter. So 1.15 Reynolds number to the 1/2, Prandtl number to the 1/3, and that's for Prandtl numbers approximately greater than 0.6. And then we have the average Nusselt number over the entire surface. And that is, again, so it's, typically we write down the Nusselt number as HL over K. So the length here is the diameter. So HD over K, and because we're talking about the average Nusselt number, we're talking about the average convection coefficient. And this one is messy. So 0.3 plus 0.62 times the Reynolds number to the 1/2, Prandtl number to the 1/3, over 1 plus 0.4 divided by the Prandtl number. And that quantity, 0.4 divided by the Prandtl number to the 2/3, and then the entire denominator raised to the 1/4. And then that whole thing multiplied by 1 plus the Reynolds number over 282,000 to the 5/8, that whole thing to the 4/5. Gotta love empirical correlations, right? And I didn't give myself much room, but this one is applicable for values of the Reynolds number times Prandtl number greater than approximately 0.2. And just as before with all the correlations we've written down for flow over a flat plate, the fluid properties evaluated at the film temperature. I'm making this distinction because we are going to write down one correlation for a sphere where you do not evaluate the properties at the film temperature. And we'll talk about why. And just as a reminder, I think we've written this down before, but empirical correlations are typically accurate to within about 20%. Of the actual value. So if you had a perfect lab experiment that you got data from and you could evaluate the convection coefficient from that data, you could expect the same coefficient evaluated from an empirical correlation to be within about 20% of that perfect value that you got from an experiment. So that's what that means. Within about 20% of the actual value if you were able to measure it in an experiment or whatnot. Okay, we're going to briefly talk about spheres. So the same kind of boundary layer dynamics that govern the cylinder and crossflow are going to be true for a sphere. You have kind of the same stagnation point upstream, the same boundary layer development under a favorable pressure gradient, then an adverse pressure gradient, boundary layer separation, and a wake forming downstream of the sphere. And of course, for a sphere, the direction of flow doesn't really affect what the dynamics are because it's going to be symmetric no matter which direction the flow is coming from. Whereas for a cylinder, if the flow is moving across the axis versus along the axis, changes whether you're talking about something with a wake forming versus something that just kind of looks like fluid over a flat plate, essentially. So we'll say boundary layer dynamics are similar to a cylinder in crossflow. And we have a couple of different expressions for the friction coefficient and the Nusselt number, or the drag coefficient. So the drag coefficient for very small Reynolds numbers which is known as creeping flow, is given by what's known as Stokes' law. And that is just CD equals 24 over the Reynolds number. And again, that's for very small Reynolds numbers of less than approximately 0.5. Very, very small. We'll also write down the average Nusselt number for flow over sphere. This one is slightly cleaner. So 2 plus 0.4 times the Reynolds number to the 1/2 plus 0.06 Reynolds number to the 2/3 times Prandtl number to the 0.4 and then we have this ratio of the viscosities to the 1/4. So this equation has quite a few restrictions on it. It is applicable for Prandtl numbers between approximately 0.71 and 380. Reynolds numbers between 3.5 and 7.6 times 10 to the 4th. And then for this value, this ratio of viscosities, values between 1 and 3.2. So when we talked about evaluating these correlations, we said that we're assuming constant properties, except the properties do change with temperature. So to account for that, we're going to assume that the fluid in the boundary layer has some temperature that varies from the surface temperature to the fluid temperature. And we're just going to evaluate its properties at the film temperature, so just the average between the surface and the fluid, to kind of account for, as best as we can, what the temperature in the boundary layer is. The other way of dealing with that is to have this ratio of either viscosities or Prandtl numbers kind of tacked on to the empirical correlation. And this is the only empirical correlation, at least so far, that we've introduced that uses this method instead of the film temperature. So for this, we want to note that all of the properties except mu sub s are evaluated at T infinity, so the fluid free stream temperature. So all properties except mu sub s evaluated at T infinity. And then mu sub s is evaluated at the surface temperature. So the fluid viscosity at the surface temperature. Okay, there's one kind of special case, kind of interesting case of this Nusselt number expression. So for freely falling liquid drops, again, you're going to have the same kind of dynamics where the sphere is passing through a fluid, and it's the exact same physics as if it was a stationary sphere with fluid flowing past it. Said it's a kind of stationary medium with the sphere moving through the medium. So for freely falling liquid drops, the Nusselt number is the average Nusselt number. Reduces to this expression. So in general, if we're talking about a solid sphere you would use this expression, the one written up here. And then only if it's specified that we're talking about a freely falling liquid drop would you use this expression. And then if you look at the way this expression is written, it's kind of interesting. As the Reynolds number goes to 0, what happens is the Nusselt number, the average Nusselt number, just reduces to 2. And that corresponds to heat transfer by conduction from a sphere to a stationary infinite surroundings. So it's kind of interesting that this expression for convection heat transfer from this situation, if you kind of say the Reynolds number comes to 0, which corresponds to a 0 velocity, then the Nusselt number expression reduces to this expression for heat transfer just purely by conduction to a stationary medium. So that Nusselt number of 2 is heat transfer by conduction from a sphere to stationary infinite surroundings. Okay, that's everything for external flow. How do we feel about it? Decent? Yeah, good. We're going to move on to internal flow, which is more complicated, unfortunately. Yeah.
Will we have to put those Nusselt number equations on our equation sheet, or would they be given in the problem?
So for the midterm, this material is not on the midterm because it's through homework 5 or lecture 13. But in general, I would expect you to have the equations that we've, kind of the Nusselt number equations that we've introduced in class and or used on the homework, which the ones that we use on the homework should only be the ones that we introduce in class, on your equation sheet. But that would be for the final. You need to worry about that, yeah. And for the final, you'll have 2 sheets. If it was like a niche equation that you hadn't seen before or something, I would give it to you. But if it's introduced in class, then you should have it, yeah. Okay. Last questions about external flow. Yeah.
So earlier you said that all properties are evaluated at some temperature, but here you said it's at T infinity. Is that just because it's a sphere?
That's because this correlation has this extra mu over mu sub s tacked on to the end of it. So there are 2 ways of accounting for kind of the fluid property variation with temperature. One is evaluating at the film temperature, and the other is to have this ratio of viscosities or Prandtl numbers, depending on the correlation, tacked on to the end. All of the correlations that we've introduced so far have used the film temperature. This one has been formulated in a way such that it uses this ratio of mu over mu sub s instead of the film temperature to account for that variation. So this is the only one so far where you evaluate all of the other properties at the free stream fluid temperature and then mu sub s at the surface temperature. And so that accounts for that variation instead of the film temperature. Okay. I'm going to start on internal flow. So there are going to be some key distinctions between internal and external flow. So make sure you've got your head wrapped around kind of for external flow, the situations that we've introduced or talked about so far are, flow over a flat plate or a cylinder, and we've always assumed that it's basically isothermal, so it's at a constant temperature for its entire length, so T sub S is always constant. And then we've got some ambient fluid, T infinity, that is also always at a constant temperature. Because those two temperatures are different, you're going to have heat transfer occurring from one to the other, right? So if the surface is hotter than the ambient fluid, you're going to have some heat transfer from the surface to the fluid. But we're assuming it's an infinite medium, right? The T infinity, it's just some kind of ambient flow, some infinite medium. So we never actually, we basically assume that T infinity is constant. So you're not going to heat an infinite medium any measurable temperature by just heat transfer from one surface, right? So that's kind of the assumptions that we developed those equations under. So constant surface temperature, constant fluid temperature. There is heat transfer occurring, but the reason those temperatures stay constant is because we've just stated that the surface temperature is somehow maintained constant. There's either heaters or some kind of maybe it's boiling water underneath it. And then the fluid temperature is always constant because it's an infinite medium. That's going to be a key distinction between external flow and internal flow. So now with internal flow, you have a finite amount of fluid flowing through a pipe or between two plates or something close to each other. And so that fluid, you are able to heat it with the heat transfer from the surface. So now instead of having constant temperatures as you go along between the surface and the flow, you have constant surface temperature, but then the fluid temperature is increasing as you move along through the pipe. Does that make sense? So you have a finite amount of fluid now. Heat transfer is occurring between the surface and the fluid, but now you're actually increasing its temperature. Okay, that's a key distinction to keep in mind. And we'll talk about it a little more as we go along. So for external flow, the boundary layer just kind of continues to develop along a plate or a cylinder without really any constraint. But for internal flow, like flow in a pipe, the fluid is confined by a surface. And that means that the boundary layer development is also going to be confined by a surface. So the fluid is confined by a surface, so the boundary layer development is constrained. And just like with external flow, I want to mention that we're just considering low speed, forced convection with no phase change. So again, the same kind of situations that we developed our boundary layer equations for. So we will have a velocity boundary layer and a thermal boundary layer, just like in external flow. So we'll talk first about the velocity boundary layer. So we'll get a sketch up here of what the velocity boundary layer in, for example, a pipe looks like. So we've got a side view of a pipe, so this is just imagine that we've cut directly through the center of it, and we're looking in from the side. We've got the inlet here to the left, so we're assuming that the x direction is from left to right. And we're going to have some uniform flow with a uniform velocity entering upstream. And so this fluid is U of R comma 0, and it's constant across the whole radius at the inlet, and it's at the x equals 0 location. All right, let's try to draw a center line. And then this is going to be our R direction, our radial direction. So again, we're looking at a pipe, a cylinder, so a circle, just cut through the middle of it. And then the radius of the pipe is going to be R sub naught. And note that we're talking about the inner radius here. So for the conditions that we're considering right now, we're either assuming that we're talking about the inner radius and we know the temperature of the inner radius, or it's just infinitely thin. Otherwise, you've got conduction through here that you have to consider. So we have some flow entering with a given velocity, and we have surfaces. So just like with external flow, the fluid at the surface is going to have 0 velocity, and you're going to have a boundary layer developing because you have differences between the 0 velocity here and the fluid velocity that's incoming. So you have some boundary layer development. And again, we're showing this in 2D, right? But you can imagine this is happening on the entire inner surface of the cylinder. And then eventually these boundary layers are going to meet in the center. So we'll say kind of this is our boundary layer thickness, delta. Of course, it's changing in the x direction. And then these are our boundary layers. So we've got a boundary layer on the upper and the lower surfaces, and then they meet. And so then you kind of have viscous effects throughout the entire flow. So now, downstream, nowhere in the pipe is the flow equal to the incoming flow. So let's draw like a little kind of cross section to see if that can.
Are you measuring the boundary layer from the inside of the pipe?
Yes.
Boundary layer thickness. Sorry.
Yes. Yeah, so this is the inner radius, this R sub naught. Does that make sense?
Yeah.
Yeah, so the boundary layer is going to be developing on the inside of the pipe because that's what the fluid is interacting with.
So like after it's fully developed, is the whole thing a boundary layer?
Yeah, I mean, you can think about it as the whole thing being a boundary layer. So kind of this, think about external flow first. So the distinction is when you have fluid that's in the boundary layer, the velocity of it is not equal to the free stream velocity. So it's affected by the surface. The fluid at the surface is 0 velocity, and so the surface is slowing it down. So the fluid in the boundary layer is affected by the presence of the surface. When you get outside of the boundary layer, you're at the free stream velocity, you're no longer affected by the surface. So here, in this region, this flow is affected by the surface, and this flow still has the same velocity as it did coming in, because it hasn't felt the effects of the surface yet.
Sure.
But then once the boundary layers meet, all of the fluid here is now feeling the effects of the surface. So it has all been slowed down from its initial entry velocity. So now it's all slower than if it were not, if the pipe wasn't there. So it's all affected by the presence of the surface. Yeah. So you can think of it as one big boundary layer. Okay, so like we were saying up here, you have some flow that's in the boundary layer that's affected by presence of the boundary layer, some flow that is still maintaining its original velocity, so that's a flat profile right there, and then going back to the boundary layer where the flow is slowing down. So the fluid in this region, the velocity of it is still equal to u of r, comma 0. So still equal to the velocity at the inlet. So the fluid here in the boundary layer, the profile is u of r comma x, so some fluid velocity that depends on the r location and the x location. But then here, that is still equal to r comma 0, because it hasn't felt the effects of the surfaces yet. So then the boundary layers merge, and then downstream of that, you have a profile where all of the fluid has been affected by the flow, or by the surface, sorry. And it is essentially parabolic. And that's why, as you probably learned in thermo or fluids, flow inside of a pipe has a parabolic shape. And so if you were thinking about this in 3D, it's like a cone, right? Three-dimensional parabola. And the maximum velocity here, or the maximum velocity is in the center because it is feeling the least effects from the surface. It's furthest from the surface, but it's still somewhat reduced from the inlet velocity. So here the entire velocity profile is some function of r and x. And this point where the boundary layers merge is a very important location. We call this x, fd, comma h, so that stands for fully developed for the hydrodynamic boundary layer. Yeah.
So once it becomes fully developed, shouldn't the velocity not depend on the x coordinate, just the r coordinate?
Yes, that's correct. Yep, after it becomes fully developed, so this is different for the temperature, but for the velocity, after it becomes fully developed, it's independent of the x location. And the velocity does not change anymore with the x location. So the shape is the same as you go downstream. Yep, thank you. So this this location, this x location where the boundary layers merge, is called the hydrodynamic entry length. So this region is the hydrodynamic entrance region. So the boundary layer is still developing up to this point. And then after they merge, the flow is fully developed. So yeah, that's kind of the key distinction there, is after it becomes fully developed, it doesn't change anymore with x. So the profile stays the same. So we'll say after x, fd, comma h, so after this fully developed location, the flow is fully developed and the velocity profile does not change with X.
Can I ask a question?
Yes.
If the, so in the entrance region, if the velocity in the middle, not in the boundary layer, is equal to the entrance velocity, and the velocities in the boundary layer are less than that, how is like mass conserved? 'Cause it seems like if part of it's, the velocity is less, then there would need to be a portion where the velocity is greater in order for the fluid to be flowing through the pipe.
Yeah, that's a really good question. So one of the key things, and what we're going to talk about actually in a little bit, is because the velocity changes over the diameter, you define it as some kind of mean velocity, and that's how you represent it. And it's defined by the fact that m dot is constant, so the mass flow rate is constant. So yeah, that would mean that this would have to be greater than u sub at the x0 location, right? Yeah, okay. So for mass conservation, then you've got some flow in the middle that is greater than the entrance flow. Yeah, good point. Definitely true. But the distinction that the flow here is kind of affected by the effects of viscosity and the presence of the surface, and that this flow in the middle is not, is still true. Thank you. Okay, anything else? We're still obeying all laws of physics? Yeah. Maybe? We don't know anymore. Okay, and this, we'll write down that this x, f, d, comma, h is the hydrodynamic entry length. So whether or not the velocity profile is still developing is going to play kind of a big role in what the slope of the profile at the surface is, and therefore what the friction coefficients and the heat transfer coefficients are. So in internal flow, in addition to having laminar or turbulent flow, which affects those things, you also have to determine whether or not you're in the entry region of the pipe. So if you're in the entry region or the fully developed region. So there's kind of like 4 different things to keep track of when you're considering internal flow. So next time we will talk about some expressions for how to determine which region you're in, and then how to calculate the Nusselt number and the friction coefficient. Thanks.